Okay, so my name's Shea Garrison-Kimmel. I want to tell you guys today about some work I've been doing with my collaborators Mike Bullen-Colchin, James Bullock, Jose Inyorbe, and an undergrad that's working with us, Kyle Lee, on high-res simulations of a local group like halos that I've been running, one of which is actually shown in the background here on this slide. So let me start off by talking a little bit about what I mean by local exactly. So everyone, of course, has a different definition from local, but it's pretty much expanded with time, right? It's gone from meaning, say, parsecs to the Milky Way to the halo around it, including the dwarfs I'm showing in this cartoon. But then SDSS came along and revealed this entire population of ultrafaints that probably extends beyond the virial radius of the Milky Way. And new LSST-like surveys are just going to push our definition of local even further out. For example, H1 surveys might find a lot of gas-rich dwarfs around the Milky Way. Now, simulations of Milky Way-like halos have to keep up with the observations by resolving larger and larger volumes with high-resolution particles. Now, when you start thinking about simulating these larger volumes, you realize that all these Milky Way-like halos that people have been spending a lot of computer time simulating aren't necessarily like the Milky Way because there's a very large galaxy nearby in Andromeda. Now, the presence of Andromeda almost certainly affects the region around the Milky Way, but it's also not clear that the local group environment that the Milky Way lives in doesn't affect its own internal properties in some ways that we don't understand. It's just an example of how surveys are pushing our understanding further and further out. On this plot, which was compiled by Eric Tollerud, we're plotting dwarfs around the Milky Way or Andromeda. And on the y-axis is the distance to whichever of those two is closer. Now in red are the gas-poor dwarf spheroidals, and you can see that they're pretty much all within the virial radius of one of the two hosts in the local group. Now, there are a few outside the virial radius, and we'd like to understand those too. Did they perhaps pass within the virial radius of one of our hosts and then leave? Or is there actually an entire population of those that hasn't yet been discovered? Now, there's also a large section here that's blank, because SDSS is incomplete there, right? But LSST is going to push that incompleteness totally off this plot and really help us figure out what the dwarf population around the Milky Way looks like. Okay, so now I'm going to talk a bit about some simulations, because simulations are potentially a great tool for understanding local group environments, right? So we ran a bunch of cosmological simulations in order to find pairs, and we selected otherwise isolated pairs of galaxies with individual masses between 1 and 3 E12, but with a sum less than 5 E12 that was separated by between 600 kpc and 1 megaparsec. We identified 880 of these in 34 70 megaparsec boxes, which means that we expect to find pairs separated by, on average, about 24 megaparsecs. First thing we did was look at the properties of these pairs, starting with the relative radial velocity of the two halos. We found that they're preferentially moving towards each other with a peak around about negative 100 kilometers per second. We then went ahead and looked at the environments that the pairs tended to live in, which we defined as the overdensity of halos larger than about the small Magellanic Cloud within 4 megaparsecs. And as you can see, they pretty much all live in overdense environments, at least greater than 1. But as per the very long tail, a lot of them live in extremely overdense environments. We also looked at the relative tangential velocities of the two halos. Found a pretty clear peak here again, around 50 to 100, but again, the horizontal axis is the number of small Magellanic Cloud, or number of halos bigger than the SMC within 4 megaparsecs, divided by the total number within the box. It goes beyond 10 as well, but cut it off there. So in the tangential velocity distribution, there is a long tail again, which probably corresponds to halos just passing by each other. But this doesn't constitute the bulk of our sample. Now the natural question to ask is how much like the local group do these pairs look? So the region in blue here is where observational data lead us to believe that the local group lives. It has a pretty average radial velocity and actually environment, as you can see. It might have a somewhat low tangential velocity. New measurements are indicating it's as low as about 17 kilometers per second. But even then, it's still not totally anomalous. We also looked for these in the Bolshoi box and found very similar distributions there. So then we took a look at the environments of isolated halos in the same mass range, and found that there's a clear difference between the pairs and the isolated halos, and that the pairs tend to live in much denser environments on the whole, and almost no isolated halos live in these extremely overdense environments. So if the Milky Way were an isolated halo and lived in that region, it looked pretty strange. Because it's in a local group-like configuration, though, it's actually pretty average. So as I said, we wanted to run some high-resolution zooms on pairs like this. Before we did that, though, we wanted to figure out what resolution we needed to run them at. So we ran the same isolated halo in a cosmological zoom at 4 different resolutions as a convergence test. As an example, the green line here is our lowest resolution, and as you can see, it stops identifying halos around Vmax of about 20, which is roughly the size of the halo that we think Draco lives in. But we wanted to identify at least all the classical dwarfs, which means we need to get down to Vmax of at least 10, which puts us on a red line here, which gets us counts down to about 8 kilometers per second. Now, this is just a resolution limit for number counts. If we actually wanted to get the internal structure of these small halos, we would have to go to an even higher resolution. And we probably will run some of our simulations at that higher resolution to get the internal structure and as an additional convergence test. But this red line is going to be our fiducial resolution. Okay, so on this 35th anniversary of Elvis's death, Elvis lives in this suite of zooms that we're running to explore the local volume in simulations. Thus far, we've selected 22 total halos in pairs, so that's 11 pairs, and for each of those, we've selected an identical mass isolated halo. We wanted to run pairs that looked like the local group, so we selected halos that were moving towards each other, giving us a range of about -200 to -40 in radial velocity. And we also picked pairs with relatively low tangential velocities, so the magnitude of that varied between about 14 and 125 kilometers per second. As I said, we ran these all at our fiducial resolution, which has a particle mass of about 2e5 solar masses and a softening length of 140 parsecs. Now this gives us up to 15 million particles in a halo and up to 42 million high-resolution particles in the uncontaminated region. So here I'm showing one such run at z of 0. The separation between the two hosts here is about a megaparsec. And I'm coloring here by phase space density to really show the rich structure that you see around one of these local group-like pairs. So as you can see in that previous one, there's very clearly 2 halos, right? So that's one way that we can easily identify that pairs differ from isolated halos. But you might not expect that there would also be differences at higher redshift. Unfortunately, it's not quite as bright as I would like it to be here. But you can see from the image at z of 7 that there's actually more structure formed in the paired sample here, sorry, in the paired run, than there is in the isolated run, even though the isolated run is mass matched to one of those halos. Another way that we might expect isolated and pairs halos to differ is in the number of subhalos and just generally halos nearby. So I'm going to plot counts here as a function of v peak, which we define as the maximum circular velocity that a halo has over its main branch throughout its entire history. And as you can see, the 2 samples really agree very well within the virial radius. And if we go ahead and scale the x-axis by v-vir of the host, and then highlight the full range and plot the average here, then you can see that the 2 populations just agree completely. Now, that's good news because it means that we expect that the number count predictions of high-resolution simulations to agree with what we find in the Milky Way, at least within the virial radius. But we've actually made sure to run these simulations with a large enough zoom region that we can go out further. So let's look at, say, 1 megaparsec, where we're actually still uncontaminated. Now, if you count halos within a megaparsec of a host, there's probably not unsurprisingly a sizable offset between the 2 populations. In fact, they actually barely overlap at all, and we wanted to figure out why that was the case. So in that previous plot, I'd be counting every single solid white circle here within the orange dashed circle as a halo within 1 megaparsec of the host in the center here. Now, that has the side effect of counting the subhalos both of that host and of its companion, which might be enough to explain the offset. So if we remove all of the hosts within the virial, all of the halos within the virial radius of either host, and count only what's left here within the orange circle again, then what do we get? Well, we find that the paired sample still lies well above the isolated sample. We see specifically a 60% offset between the two. Now, this isn't too surprising, right? Because we already showed that pairs tend to live in denser environments. It wasn't obvious, though, that this would be the case down to the lowest masses that we can resolve here. So this makes the point very well that if you want to predict what LSST is going to find in this region, in the 1 megaparsecs outside the Milky Way in M31, you cannot use a zoom simulation of an isolated halo. Okay, so in summary, new surveys like PanSTARRS, SkyMapper, DES, PANDAS, and eventually LSST, and so on and so forth, either are or will push the boundaries of what we think of as local to larger and larger distances. Now, simulators need to keep up with the observers, which means resolving larger and larger regions around halos like the Milky Way, and furthermore, placing the Milky Way in its proper cosmological context, specifically with a large mass halo nearby and approaching it. One interesting result that we found when we went looking for these pairs is that the overdensity of galaxies brighter than about the SMC within 4 megaparsecs actually isn't unexpected for halos that live in LG-like configurations. So motivated by the ever-increasing volume that surveys are covering, we're creating the Elvis suite, which consists of 44 halos so far, half of which are in local group-like environments. And the main purpose of this talk was really just to describe the set of simulations that I'm running, because we have a lot more things that we're starting to look at in this data set, some of which I'll probably be presenting here next year, actually. We're, of course, open to suggestions as well, but one nice result that we do already have is that within the virial radius, subhalo number counts agree between the isolated and paired runs. We've also found that pairs of halos tend to live in denser environments and otherwise isolated halos of the same mass. Specifically, we predict about 150 galaxies larger than Carina outside the virial radius of the Milky Way or M31, but within 1 megaparsec, versus only about 90 were we to live in an isolated galaxy. And that's all. Thank you.